Well, yeah, thanks again. So what I would like to talk about here is some work that I've been doing with a few folks to understand these new volunteer programs that are being used in emergency medical services. It's something that actually the idea has been around for some time, but it's really with the advent of smartphone apps that this has really come into its own. So this is joint work with Caroline Jachtenberg and Peter Vandenberg, who are both in the Netherlands, and then Maggie Lee is a PhD student here at Cornell. So let me get underway, but actually let me mention one more thing before we get underway. So there's not a huge amount of queuing in this talk, so sorry about that. And oddly enough, there's actually not a lot of data either, but I think the presence or absence of those things you'll find kind of interesting. And I think you'll find the application kind of interesting as well. And there are actually links to queuing that I'll try to bring forth later on in the talk. Okay, so what are these apps and how do they work? So in this picture that I'm showing you right now, we've got some poor guy over here near the cursor in the bottom left, and he's just having a cardiac arrest. So I should clarify, cardiac arrest is different from heart attack. So cardiac arrest is when the heart goes into a bad rhythm. Heart attack is when there's a blood loss. There's the blood flow to some part of the heart is cut off. So anyway, this guy's having a heart attack. And so somebody near the scene puts in a call to 911. And that's represented by that arrow going up there. So the call center for 911, they log the call, they grab some details from the person calling, and they will fairly quickly triage that this is a cardiac arrest. And then what they'll do is they'll alert an ambulance that's sitting up there in the top right corner at a base, but they will also activate this smartphone app, which will then alert those volunteers who are close to this patient. And that's represented by these arrows. Now, some of these volunteers won't accept the alert. They are unavailable. So that's what's going on here. So that volunteer is not going to respond, but the other two are willing to respond. And so what will happen is one of those two people will accept the alert. And let's suppose it's the closer of those two people. And then all those people who have accepted will respond. And the goal is that these volunteers will be dense in the city. And therefore, they'll be much more likely to be close to this cardiac arrest and be able to render high quality first aid, which is CPR basically, and do that before the ambulance. And we'd all love for the ambulance to arrive quickly because they can do many more things like administer drugs and so forth. But typical ambulance response times are going to range anywhere from like 6 minutes up to about 15 minutes. And that's really getting to the outer edge of the range of response times that you want. So that's what these things are, and they exist right now. So what I'm showing you in the top left corner there, you don't really need to read it. It's just the web page of an organization called GoodSam that's based in the UK. And they've created this app that runs on people's phones. And then that technology has been sort of distributed throughout much of the world. So here on the next page is the GoodSam web pages for St. John, which is the ambulance service that runs in Auckland in New Zealand. And it's not just restricted to maybe the former Commonwealth or something. There's also another parallel effort called Pulsepoint in the US. And this is essentially the same idea. So the goal of these volunteer programs is to decrease that first response time, to increase cardiac arrest survival rates. But it's not just cardiac arrest that these methods are being used for. It's also other kinds of urgent calls. So in New Zealand, it's purely for cardiac arrest, but for some of these other countries, it can be for trauma of some kind. So an ambulance is still going to respond to every call. So it's not that the volunteers are taking over from the ambulance still responds. So the workload for the ambulances looks about the same as before, but you hope that survival rates are going to go up. And this idea has been around for a little while. It's getting a lot more attention in just the last few years with several articles in the journal that I've mentioned here, Resuscitation. And those are primarily empirical studies. And what we're doing is a kind of a modeling study to analyze these things. So the research questions that we want to look at for today in this talk are, what's the impact of a certain number of volunteers on the first response time? What's the impact on survival rates? And one of the things that makes this difficult is that ambulances are supposed to be centrally controlled. You know, sometimes the drivers have their own ideas, but they're supposed to be centrally controlled. And so we can direct them where we want them to go. But volunteers are doing their own thing. They are volunteering, and therefore they're living their regular lives, going to their regular jobs, going home at whatever time they feel like. So they're not obligated to be anywhere at a particular time, and they're not obligated to respond. So how should we capture their contribution? And the short version of this is that we're going to use Poisson point processes. And then for some reason, I'm going to bring out the idea of optimization as well. So why point processes? Why Poisson point processes? Well, I'll explain that next. Then I'll talk about how we can model the response times of volunteers in conjunction with ambulances. Then the case I'm going to make is that the data that we have on these volunteer schemes is somewhat sparse. I'll tell you what we have, but it's sparse, right? So it's hard to do much in the way of estimation using that data. So we're going to use optimization in lieu of that. And I'll talk about how to do that for two different performance measures that I'll mention later. And then I'll sort of wrap up by saying where we're going with all of this work, because it's really, you know, there's just a large number of modeling questions that we want to look at to help this industry. So why Poisson point processes? So here I picked some random location in the world. Yes, University of Melbourne was chosen deliberately. But I actually have no idea what this part looks like. I would have to sort of be on the scene to figure that out. But let's suppose that somebody's here and they experience a cardiac arrest, right? So the app is going to look for the volunteers that are within some radius that you can configure on the app. And let's say that that's this radius here. So it's looking for any volunteers that are in this immediate vicinity. And on this particular day, let's say we have volunteers at each of those funny little ellipsoids, which are supposed to be halos for angels, right? So on this one particular day, there happens to be one person who's reasonably close to that call, so that's good. And that person could respond if they accept the alert. On a different day, you might have volunteers in a different set of locations. So the number of volunteers that are in that immediate vicinity is random. So how do we model its distribution? Well, we've got a lot of volunteers, hopefully over an entire city, we've got thousands of volunteers. And each volunteer has a small probability of being in that circle. And so that should be giving you a hint as to where I'm going with this. So N volunteers in total, and you should think of N as being in the thousands, potentially the tens of thousands. And we're assuming that those volunteers are not coordinating in any way, which I think is pretty reasonable. Each has a very small probability of being in that circle. And so the number of volunteers in that circle is binomial with large N, small p. And we know that that's approximately Poisson. So we're going to model the number of volunteers in that circle as being Poisson distributed. You might say, wait a minute. So some volunteers might spend time on the Melbourne campus, but some volunteers will be always spending their time elsewhere. So each volunteer may have a different probability of showing up in that circle, and that's okay. Lecam's theorem tells you that you still get in the superposition something that's approximately Poisson. And then you might also say, well, wait a minute, each volunteer has just a completely different location distribution for where they are distributed across the city. And it turns out that once again, just using very standard ideas from point processes, this number of volunteers in that circle is still going to be approximately Poisson. So at any given moment, what we're going to do is we're going to model our volunteers who are living in this city C. C is like a region in the plane, is the way I'm thinking about it. We're going to model those as a Poisson point process with a mean measure that looks like this expression up here. So it's got the N parameter there, that's the raw number of volunteers. Alpha is the probability that a volunteer will accept. And if you know something about Poisson point processes, you know that here I'm just thinning a Poisson point process to get another one. So the intensity of this Poisson point process, or the mean measure, sorry, is related to n alpha. And then we have this nu at the end here. This is the conditional probability measure for the location of a single volunteer who is available, right? So this is going to be my mean measure for how I capture where are all these volunteers. So the consequence of this is that when I look at the raw random number of volunteers, capital N, that's in any set B, that's Poisson distributed with a mean that looks like n alpha times nu of B. And this nu, again, is a probability measure. So that's a number between 0 and 1. And then the n alpha you could think of as being the expected number of available volunteers. So that's giving you some reasonable parameter for the Poisson. And then the really nice thing about this is that, and this again, all very standard, the probability that there are no volunteers in that set is the probability that a Poisson random variable equals 0, which is just this exponential that you see here. Okay, so how do we model response times? So the idea here, what's a response time, right? It's the time, it's basically the time until somebody arrives to help. So let's let R be that random response time, and let's compute this probability that that number is greater than some threshold little t minutes. And if we do this for a bunch of different values of little t, we've got the full distribution of the response time. So in order for the response time to be greater than t minutes, any ambulances that are stationed within range of this cardiac arrest must be busy. And there must be no volunteers that are no available volunteers, those who are willing to accept the alert. There can't be any of those in the neighborhood. Well, that's just this probability. So we have, for each ambulance, we're assuming that they have, they're busy or not independently. And so that if they're busy with probability Q, the probability that all K ambulances that are based nearby are busy is Q to the K. And then we multiply that by the probability that there are no volunteers available in the neighborhood. So this assumes that individual ambulances are busy or not independently from one another. And that's not true, but it's a reasonable approximation that's used in lots of modeling in the ambulance services. So we're going to use that. And this B here is just the neighborhood within which volunteers could respond within time T. And so this is all for one location. So there's a K for that location, and there's a set B for that location. The alpha could be specific to that location. But then what we're going to do is we're going to sum up over all call locations, weighting by the probability that the cardiac arrest happens at that location. And so that allows us to compute stuff like this. So this is the cumulative distribution function of the response time, assuming different densities of volunteers. So when you're looking at these curves, we've got response time on the horizontal axis, and we've got the cumulative distribution function on the vertical. And what's happening here is we're just plotting different curves, assuming different densities of volunteers. And you notice that all of these curves are anchored at the left-hand side at 3 minutes. And that's because in this work, we're assuming that there's a 3-minute delay from when the cardiac arrest happens until the volunteers are notified. So that includes somebody realizing they have to call 911 and calling 911, and then the call taker logging the details of what's going on and realizing that this could be a cardiac arrest, and then activating the app. So that's a 3-minute delay. So we can't get less than that. At least that's our assumption. Now, in real life, there could be somebody who's actually within eyesight of somebody who collapses and therefore can deliver a faster response time, but that's not in our modeling. Okay, so the thing that we really care about, though, is not the response time, but actually the probability of survival. And it turns out there's a bunch of curves that have been estimated for the probability of survival in the literature. And here what I'm doing is I'm stealing a picture gratuitously from this nice paper by these folks in the bottom right corner. So they're all great folks that have worked in the ambulance industry for a while. And they did a survey of the literature to find these survival functions. So each of these survival functions is based on some kind of study. And the best of these studies involved a study in a casino. You might have heard of this, where because the casinos have so many cameras on the floor, they were able to observe patients having a cardiac arrest and then observe when first aid was first being administered. And therefore, they could very accurately measure the response time and then look at the survival rates post-hospital for that episode. So that's kind of one study, but then there's been a bunch of these studies, and most of them are based on using some kind of logistic regression. So they all have similar functional forms, but they all look like this. So if the response time is 0 minutes, you still don't have very good outcomes, maybe 30 to 50% survival rates. But if that response time starts to creep up, then this probability of survival is dropping. And one of the things I should note is that we're using DeMaio and Farlevine mostly. So the Farlevine actually relies on 2 response times. It's the time until CPR, and it's also the time until defibrillation is administered. And we'll talk about those 2 dimensions a little bit more later. But essentially what we're going to do is we're just going to take this response time curve. We are going to use that to figure out the density of the response time, and then we'll do some kind of integration against the survival curve to get survival probabilities. And that's kind of the heart of the calculation. We have to do it carefully so that it's efficient and we can do the calculations rapidly, but that's the sort of core of the idea. And again, just as a reminder, we look at a 3-minute threshold for that response time. And that means, for example, if we're using DeMaio, which is the dark black curve here, we're not going to be able to beat 18% as a survival rate, no matter how many volunteers we throw at this problem. So when we are extending this idea that I've just been explaining to the whole city region, it really is just we just need to compute these quantities across the whole city. And an ingredient for that is this volunteer location measure. And that's something that we don't know. So we would like to get that from data. So that would be the typical approach to doing this. So that would be the sort of traditional scheme. But let me tell you a little bit about the data that we're seeing from St. John. So St. John has provided this to us. They've given us all their data on GoodSam. They've been operating since 2017, late 2017. And obviously this overlaps heavily with the COVID stuff. But anyway, we have that data. We also have out-of-hospital cardiac arrest data for quite a lot longer time span. And that means that we can estimate the probabilities distribution for the location of cardiac arrests pretty well. But we can't estimate the volunteer mass, that new quantity, very well. Why is that? Well, for each of those cardiac arrests, what we know since November of 2017 is the time of the arrest, and then the location of the cardiac arrest and the alerted volunteers who were close by. So just those guys. We don't have ongoing information about all of the volunteers, like where they're spending their time. And that's for privacy reasons, right? So those locations are not logged in the system in any way. And there's, it's very clear that you have to stay away from that, because otherwise volunteers are delivering very highly personal information about their location, and they won't be willing to do that if we were to get more involved in that data. So we just have that information. So the locations are dithered, by the way. We did this. We set up the formulas for St. John to implement this. That's really just to ensure that we're guaranteeing privacy of those people who are having cardiac arrests. So we just shift not just the cardiac arrest location, but also the volunteers who are nearby. They all shift in the same way. That's the reference to CRN. If you're a simulation guy, that's common random numbers. So then we also know which alerts were sent and the outcome of those alerts with each volunteer. But this is just too sparse to infer the volunteer distribution. We are trying, but we just are pretty sure it's too sparse. So what can we do? Well, one option is to pick a reasonable distribution for where are the volunteers. And what does reasonable mean? Well, we can argue about that. The other approach that we're doing is we're using optimization to actually choose the volunteer location distribution to maximize the survival rate, or to minimize the fraction of response times that exceed a threshold. So we're actually using optimization to do that. That means that we're playing with this thing that really we don't have control over, not direct control anyway. And we're doing that because it gives us bounds, and those bounds can be useful in telling us what can be achieved. Because what we can tell you is that with a certain number of volunteers, you're not going to get performance better than a certain threshold. You won't get survival rates above 12%, say. And then that's useful because that tells us, should we be recruiting more volunteers or should we not? So how does that optimization work? Well, it turns out it's a convex optimization problem. So if R again is that response time, but now it's a function of this location probability measure, what we'll do is we'll consider both this probability that that response time exceeds a fixed time. Think of that as being 5 minutes or something. So think of little t as being 5 minutes. But we can also look at survival, and I'll mention that in a second. And the next step is not essential, but this will simplify matters hugely. So let's suppose that this probability measure is discrete. So we lay a sort of a net over the city, and we just assume that volunteers can be at those locations. Those probabilities of being at each of those different locations are now my decision variables. And this function is convex in those probabilities. And why is that? Well, it sort of comes down to this calculation here. Lambda sub L is the probability that the call shows up at a particular location L. And then this exponential term here is the probability that there are no volunteers in a neighborhood of that particular location, right? So I'm just adding up the probability mass over the nearby locations here. And then I've got the n alpha that is the same as before. And then this is just that exponential form. And when you look at that expression there, you can see that that's convex in the new variables. So we want to work with an expression like this. This is the probability that the response time is bigger than t. I want to make that small. So I'm wanting to minimize this. Over the choice of those new variables, I'm minimizing a convex function. So that's a tractable optimization problem. If we're thinking about survival probability, remember that's the sort of an integral of these response time density against the survival probability. That turns out to be concave. And in fact, so that's good news, right? Because concave maximization problems are straightforward. So that's good news. That means that the optimization problem is tractable. And so that means that I can get an upper bound on the probability of survival as a function of n. It's an upper bound because I'm choosing the volunteer locations. And then that upper bound then informs the recommendations for policy, like how many volunteers do we need. So the allocation you get by maximizing for survival is different from the allocation you get for minimizing late calls, right? So late calls, those that have response times outside a threshold. So here's an example that shows that. So I have 3 locations. I have 2 demand locations, each of which has some demand rate lambda. And then I have some volunteer location potentially right in the middle between these 2 guys. So that's this guy. So volunteers can be at one of 3 locations, these 3 sort of dots here. And if I'm trying to minimize the fraction of calls with response times outside some threshold, well, if from that middle circle I can reach those outer points, then it's optimal to put all my volunteers in the middle because they can reach those points within my time threshold and I'm done. And I want them, then basically the properties of Poisson's are that it's best to sort of lump all of your mass at this, this light blue point. But if I want to maximize survival, this time that it requires to respond from the light blue circle out to one of those points might be quite long. And you saw that those survival curves are convex and decreasing. So by the time you get there, there may be very low probability of survival. And that means that it may be optimal to distribute your volunteers to the 2 locations. So what this means is that the allocation of volunteers that you want is not the same in the 2 cases. So let's just take a look at an example in Auckland. So this is the data that we have. So I'll zoom into Auckland there. So this is what Auckland looks like. You've got this sort of isthmus through the middle here. It's surrounded by sea. So the white stuff is the sea and the colored stuff is land. There's more land up here, but I've sort of cut it out of the map. Anyway, so this is what Auckland looks like. And what we're looking at is the population density. So that's the inhabitants per square kilometre. And we've broken down Auckland into its area units, which we obtained from, I don't know, census of New Zealand, I think. And so you can sort of see that this is the central area. This is a central business district. It's the densest part. But there's also these other pockets where you have high density of individuals. And then you have these sort of more rural areas that are, and this is all sort of suburban up here. So lower density in the suburban, but certainly high density pockets. So what we're going to do for these calculations that I'll show you, volunteers are walking 6 kilometers an hour and they're going to walk a distance that is as the crow flies, straight line distance. You could certainly argue with this in many different ways. You might say, well, maybe volunteers would be driving, or maybe they would be riding a bike or something. And it turns out actually in London, where there's such a system like this in place and has been for a while, it's illegal for volunteers to drive. The thinking is that volunteers get kind of excited and they drive kind of silly, and they could cause more trouble than you've begun with. So volunteers are required to walk or run. As the crow flies, that's a questionable assumption, I think, but not too bad given that people are walking. So we're assuming this delay till volunteers depart is 3 minutes. That we think is plausible. We have data on this, but the data is pretty noisy. We're still figuring all of that out, but that is not unreasonable, put it that way. The delay until an ambulance departs is shorter, and the thinking there is that somehow volunteers might take a little bit of time to activate themselves, and ambulances are supposed to be quick at this. So we've got in Auckland, typically during the day, something like 25 ambulances. We're positioning them using an optimization algorithm that optimizes positions for ambulances. But we could just take the actual locations that ambulances work. It doesn't really matter for the purposes of this demonstration. But the MEX CLP is just an optimization algorithm it's a formulation that does a good job of placing ambulances. And then we obtained travel times from a friend who works on this stuff down in New Zealand. And what we're going to do here, because we are not sure about the volunteer locations, first of all, I'm just going to fix it as being proportional to demand. So demand for out-of-hospital cardiac arrest. So later we'll do some optimization, but just assume that the volunteers are positioned somehow in proportion to demand. And here's kind of the pictures that are straightforward to compute now using the ideas we've just talked about. So in the left-hand panel, I'm showing you the fraction of late arrivals as a function of the number of volunteers on the horizontal axis. So here it's the expected number of available volunteers. These are the ones that would accept an alert. And I have 2 thresholds, 13 minutes and 7 minutes. So the probability that my response time is greater than 13 minutes is decreasing extremely rapidly as I increase the number of volunteers. And that makes sense, right? With enough volunteers, you're filling up the gaps in the city, and so that's going to drop. But with a more stringent threshold of 7 minutes, it's slower to improve on that threshold. And that's just because you need a greater density of volunteers to fill the gaps. And when you look on the right-hand plot, here again, I've got the expected number of available volunteers, and now I'm plotting survival probability. This dashed line is that cap that we can't beat. What you see is this thing growing, but it's growing incredibly slowly. You know, even for 5,000 available volunteers, we're only getting to a survival probability of about 13%. So what this is telling us is that you really have to, you need a lot of volunteers basically to have a big impact on survival using this particular survival curve. And this is one where it's just based on time till CPR, right? So it doesn't include the time to defibrillation. We can do other calculations. On the left-hand side, I'm showing you the probability that a volunteer will arrive first as a function of the number of volunteers. And basically, you don't need too many volunteers to be sure that you beat the ambulance to the location. And that's just a fact, right? We're all stuck with this no matter where we live. On the right-hand side, I'm showing you the curves that we get from 3 different measures for the volunteer location. So there's the survival optimizing, that's the bright green. There's proportional, which, I mentioned it's sort of proportional to the demand density. And that's basically on top of that optimizing curve. And then the other curve there is just another allocation. And what you see there is that the probability measure well, there's some robustness here, right? If the volunteers are really just distributed roughly proportional, at least according to this picture, it looks like it's pretty close to optimal. So if we dig in a little bit just to say, well, how do these allocations differ? So what I'm showing you here is a different plot. On the horizontal axis, I've got the probability density of it's the probability of seeing a call, that's the lambda L, but I'm dividing by the area of the local region. So I take an area unit and I compute its probability that it's going to contain the next cardiac arrest, but I divide by the area of that region. So that's what's on the horizontal axis. On the vertical axis, I've got how much probability density in the volunteers am I allocating to that region, again, normalized by the area of that region. So what you're seeing is each of these dots that you see, each of these circles, is take one of those area units in Auckland. It's got a demand density that's on the horizontal axis, that's its coordinate, and it's got a probability that we allocate to it that's on the vertical axis, and we plot a dot. So we do that for every area unit in Auckland, and we get these curves. So maybe just focus in on the proportional, which is the straight line you see in the middle. That's what you would get if proportional were optimal. You would have all of your area units having an exact mapping through that line. And the optimal choice depends on how many volunteers you have, and it has this kind of interesting shape. So what's going on is, look at this one here. So this is when I have very few volunteers. I only have about 500 volunteers. So what happens is we allocate no probability mass to a bunch of these area units that are that have very low probability density. But then as the probability density increases, we are allocating some volunteer mass to those locations. And it ends up being roughly proportional up here and then sort of curving down here. But when I increase the total volunteers that I have, the total mass of volunteers, it starts to sort of move above proportional initially, but then drop below. Now I'm making a big deal of this, but really what's going on based on that previous curve is that, you know, the adjustments from the straight line are not buying you that much. So so that's actually good news from the perspective of impact. It means that we're going to be able to, you know, there's a robustness to this volunteer distribution. So why is proportional not optimal, and why do you see those shapes? Well, I've got a sort of a stylized example here. I think what I might do in the interest of time is, I think I'm going to skip it. I guess I'll just say the following, right? So in this example, I have two locations, and what's going on is I'm looking at the optimal allocation of volunteers to those two locations as a function of the number of volunteers. And the shape of the curve does indeed change as you change the number of volunteers. And that's what we saw in the previous curve. So I'm just going to skip the details. Up till now, what I've just shown you are results where we're modeling survival rates just based on CPR. So what if somebody does actually apply defibrillation, right? And so in this slide here, what I'm saying is, well, suppose that ambulances defibrillate, but volunteers cannot. That's not true. Some volunteers can, but suppose it's of this form. So now we have two response times, the time till CPR and the time till defibrillation. And the CPR happens either when the volunteer gets there or an ambulance gets there, whichever happens first. And then defibrillation happens when the ambulance gets there. The survival curve is now a function of both of these estimates. And the good news is that as long as that survival curve does reasonable things, right, the survival probability is decreasing in these times, then once again, the optimization problem that we want to solve is concave. It's a maximize concave function, so we can solve it efficiently. So that's good news. We can work with both CPR and defibrillation by ambulance. And we can compute stuff, so I'll just skip the details. Maybe this one I want to show. On the left-hand side is the optimal allocation of volunteers to locations if you're optimizing for a threshold response time. And since this talk is all primarily focused on cardiac arrest, that's not really the thing we care about. But remember that these volunteer schemes are being used for other kinds of calls in locations other than Auckland around the world. And so there, it is actually very important what that threshold is. And so there we can easily compute that stuff. But it is striking how different these optimal allocations of volunteers are if you are optimizing for survival, which is on the right-hand side. And we are in this expression on the right-hand side, we are optimizing for survival, where we're also taking into account the fact that you have some ambulances at these stations. So it may be a bit hard to pick out, but those little circles that I'm indicating are the number of ambulances that are stationed at those locations. And so those are they are the real bases for ambulances in Auckland. And these little circles are telling you how many ambulances we allocated to those locations. And what you see is that where you have an ambulance based, you have fewer need for volunteers in the very immediate vicinity. But it's not universally the case. So over here in this region, you have three ambulances there, but you actually have quite a high volunteer density. And the issue here is it relates to sort of the travel times by driving. They're not very good there. So you see sort of features like that. So one other thought though, what if you have volunteers who are a bit more sophisticated? And the person with whom we're working at St. John is such a person. So she is a volunteer. She has responded to give CPR, but she also has her own defibrillator. And so she has applied defibrillation. So suppose we have two kinds of volunteers, one that can only apply CPR and one that can apply defibrillation as well. So we have two location probability measures, that's nu up here and omega. Ambulances do both of these things. Now it turns out we need to impose some structure on the survival function because there's a kind of an interaction that wasn't there before. So if this survival function is submodular, and don't worry about the details, this is just, the main thing is that you kind of need some additional conditions, then the survival probability is jointly concave in these two location probability measures. And if you have, say, 300 locations around a city, this nu here is 300 dimensional, so is omega. So this is a 600 dimensional problem, and this probability is jointly concave in those two guys. And then it's sort of quite efficient to optimize over both of those probability measures. If we don't have the submodularity, then it turns out that all we can assert is that this probability of survival is marginally concave in the 300 dimensional vector nu, and marginally concave in the 300 dimensional vector omega. So optimization is harder, but there's still some hope. So just coming back to Auckland for a second, how many volunteers do we need? This is the kind of thing where we can start to help St. John in a concrete way. So they have, let's say, I'm making this up. So from our curves, let's say they have 5,000 volunteers that they're aiming for that are available at any given time. Right, so they're hoping for 5,000 available volunteers. And let's say, and here I'm picking a number that's very small, this is the alpha. This is the probability that a volunteer will accept the call. In London, this number is closer to 0.5, so about half of the alerts are accepted. In Auckland, it's much lower. I won't say how it relates to this 0.14, but that would imply that you need 36,000 volunteers. So that's 2.5%, that's 2.5% of the Auckland population. So that's a lot. But these volunteers really just need to be able to do CPR. And so there is hope for this. And in fact, in the Netherlands, in an early version of these programs, more than 1% of their population was registered as a volunteer. So in our case here, we know how those volunteers ought to be allocated across the city. We can't really control that. But what we can conclude from what I've just said is that you need at least 36,000 volunteers, and we don't know exactly how many more. But fortunately, this proportional allocation, which we think is pretty reasonable, it may have its shortcomings, but it's not bad. That's probably pretty close to optimal. So that 36,000 might actually be a pretty close estimate of the number we need. We can also use the techniques that I'm showing you here to suggest where we might want to grab more volunteers. I won't go into the details of that, but it's very straightforward. It's just looking at the optimization. And the other point that I want to make here is that boosting that 0.14, which is the probability that a volunteer will accept the the alert, that has major impact because that effectively changes the number of available volunteers you have. It's kind of like saying that these 36,000, we convert them by multiplying by 0.14. If we're multiplying instead by 0.3, boy, does that have an impact on the number of active volunteers in the setup. So some of the current and future work that we're dealing with in this problem relate to these questions. So if we have several types of volunteers to recruit, which ones should we go for? And what we're doing here is we're saying that the type of a volunteer relates to, say, their home address or their work address, say. And then what we can do is we can look at that address and then look at where else they spend their time. So volunteers who live in an area unit actually have a profile across the whole city. You can think of that as being a vector of probabilities that they're in these other locations. And it'll be concentrated around their work or home address, but they'll spend time in other areas as well. And then if we have those profiles, it turns out it's pretty straightforward to just optimize how many volunteers we want to recruit who have a work or a home location in one area unit. And so we're working on getting smart graph or Facebook data for this. It's a bit challenging because New Zealand doesn't have smart graph data. The Facebook data may help us if we get approval for that. So if we have those profiles, then we can optimize over those and then help dramatically with the GoodSam in New Zealand to determine where they should be recruiting. There's another question or a bunch of questions related to the dispatch policy. So when you get a cardiac arrest and you have a bunch of volunteers around there, which ones do you alert? You can alert all of them if you want, and that's fine. But it could mean that you end up with many volunteers responding, and that wastes a lot of volunteers' time, and that creates frustration. So we want to kind of set it up so we get kind of 1 or 2 responses, but not too many, so that they don't end up stepping on each other's toes. And there's another complexity there. Like, what if somebody who's, say, 500 meters away responds and says, yes, I'll respond, and you haven't yet heard from the person that's 50 meters away or 100 meters away? What do you do? And so what we're doing is we're looking at those kinds of questions using dynamic programming kind of ideas. It's challenging. The state space, as usual, is big, but we're doing what we can. Maybe you should redirect, if you have a couple of volunteers who respond, maybe you should send one to go and pick up a defibrillator on the way. One idea I'm particularly excited about, because I've spent a bit of time at Lyft and have a lot of pals at Uber, or Didi, I guess, is should they carry defibrillators, and should we alert them to go to these calls? And I think there's going to be a lower level of altruism if we try to rely on those guys. And so if we have to pay them to do that, how much is that worth in terms of, well, what would we get as marginal improvement in survival rates? So that's another very important question that we want to look at. There's also, you probably have heard about these studies where unmanned aerial vehicles are being used to deliver things. So my friend Tin Chan at Toronto is doing that kind of work. how much of a benefit is that? It's probably not going to work in a city in the near future, because you can just imagine, right, these vehicles driving around in a city, it could be chaotic, but in a rural setting, it might actually be pretty useful. So, and then sort of looking much further out, like suppose that these volunteer programs really catch hold to the extent that they actually grow quite dramatically. Maybe we should be thinking about redeploying ambulances in response to what we see from a volunteer probability distribution. So I think that was all that I had to say. I'll stop there and open it up.
Thanks very much, Shane, for a fascinating talk. If people have questions, perhaps you could put them in the Q&A, please.
Thanks, Ruth.
Let's see, Peter Taylor has a question. So Peter, perhaps you could unmute and
Thanks, Ruth. Yeah, my question was a little bit complicated to put in that Q&A, but so I was lucky enough to see Shane give a version of this talk last year. It was that last time I actually travelled anywhere, when we were in Auckland for a workshop. And I have to say it had a big effect on me. And one thing I did when I got back to Melbourne is work out where the defibrillator is in our school. So I do now know the answer to that. And I'm not qualified to use it, which is to my shame. And one of the things I need to do is go and work that out. But I still think, assuming I am qualified and I know where it is, the actual detour I would have to make to go and get it, I think still would be significant on the timescale of 3 to 5 minutes that we're talking about. I mean, is that, I mean, you mentioned that, okay, maybe the first responder goes straight to that and the next person might go and get the defibrillator, but is there evidence that that actually is a useful thing to do?
The best evidence that we've got for that, Peter, is these survival probabilities as a function of the two variables. So those are all based on empirical studies where people have done their best to measure the times to both defibrillation and the time to CPR. So if you do look at those joint functions, the most important factor is how quickly something starts to happen for the patient. High quality CPR is a big determinant, but that defibrillation is a sort of a step jump. It really does make a difference. But if you were facing this, the best thing for ensuring the survival of the patient is for you to stay with the patient and then send somebody else, or vice versa, right? So as long as that patient's getting good quality CPR, it's the best thing.
Right, and there are now relatively transportable portable defibrillators that some people carry around with them all the time, aren't there? Or is that wrong?
There's some that are slightly bigger than this cell phone. So yeah, so it's kind of remarkable. So one of the things that's being considered is to buy those defibrillators for the volunteers. And they only work once and then they're shot because they're delivering a pretty massive current and then they're sort of done. So the idea is, if they're cheap enough, maybe you just hand them out to a whole bunch of volunteers and they just keep them with them. So yeah, that would be great. And then, you know, once again, we can try to quantify the impact of those things.
Thanks, Shane.
Yeah, thank you, Peter. Yeah.
So Shane, a question occurred to me. Is there an effect of communication delay or decision delay? You mentioned, you know, trying to optimize who would respond and that kind of thing. That requires a decision to be made, right? How big an effect is that?
Yeah, that's fair, Ruth. So so the way that it works, right, is that somebody is kind of shocked that somebody's fallen down in front of them and takes a little while to react, but then hopefully fairly quickly calls 911. There's very little delay in calling 911 because obviously you set that up so that you get very quick response times in the call center. But then there's this period, typically there's a sort of a 2-minute, something on that order period, where the call taker in the call center is trying to figure out what is it about your particular emergency. And so there is a period where they're going through that, but they're going through a script. And that script varies from some places to others, but it's a very sort of standard script. And it's designed to very quickly identify these kind of urgent calls. So there are these sort of delays at that first part of the process, but when they click the, you know, alert the participants, that's as fast as the cellular network is going to allow. And we haven't really studied that to understand exactly what those delays look like. There could be some variability there. We don't know. So we've taken this kind of simplified approach, dramatically simplified approach of assuming 3 minutes. But you can sort of see, you would have seen through all of the technical side of this that we can easily handle a random delay at that start mathematically, but larger delays are kind of brutal, right?
Yeah. And I guess deciding which volunteer should go, does that take time, substantial time, or?
No, that's pretty straightforward, because right now what they do is they just alert a bunch of volunteers, and then anyone who responds just goes. Like they don't actually cancel. There's no decision logic at that point in their current dispatch system. So luckily, no delays there. But they do express this reluctance to alert too many volunteers, because they just don't want too many to show up. So you create this kind of binomially distributed number of people who are willing to respond, who might respond actually, volunteers. So they would like the number of volunteers who respond to be deterministically equal to 1, but it's hard to do that with a binomial with small n and potentially large p.
So I guess somebody was asking, is there an effect of the message sent to volunteers? For example, there are only 2 volunteers close by, please respond soon. So I guess at the moment they're not sending that kind of message. Is that right?
Yeah. Well, first of all, I love that question, right? So, I mean, that's absolutely the right kind of question. And no, they're not sending those kinds of alerts, but anything that they can do to boost the alpha, the probability that the volunteer accepts the alert, is going to have a big impact. So I love that question.
Yeah, you don't want volunteers to waste their effort. Okay, this was great. So we now have a 5-minute break, and then we'll be back with the next talk. Thank you very much, Shane. Hopefully we can have like a virtual.
Yeah, thanks, Ruth.